There's a whole bunch of processes that you can find out in natural systems where there's a chain of different transitions between states. For example, when you have the disintegration of a given radioactive material, usually you go into one class of atom into another that is unstable again and goes into another kind of atom. That could happen also within metabolism, right? We have changes and transitions between different metabolic species. And in this lecture, what we want to show is what's the minimal mathematical treatment that you need to address that kind of processes that are very general. And I just put here two examples of relevant examples that you might want to see. One is something that we'll discuss later on, has to do with the colon crypts. Crypts in the colon are a very interesting kind of system, right? Specific part of the architecture of the tissue that can be seen as modules where you have essentially three classes of cells. As usual, this is a simplified picture. Stem cells, right, that proliferate and create another kind of cell that is partially differentiated or can replicate. Is the transient cells, right? It's another part of the crypt, okay? And then these differentiate themselves into something that is just the ending state. They cannot replicate anymore. And in a way, you can imagine this as a push system that creates a linear change of events, which end up in the cells on the tip that are just delivered and lost, right? Dead cells. Okay. When you make a microscopic sampling of this, for example, you make a section here, what you will see in the microscope is a characteristic image of the colon tissue where the sections are like this, right? This is for the healthy colon, right? Where you have here the surroundings here. This is what's called the lumen. And this is a characteristic picture of this kind of modular architecture. But the thing is that this is a homeostatic system that has proliferation, has depth, and has an architecture that we can describe in a first approximation as a linear chain of events. Another example would be, for example, protein folding. Right? When a protein folds, essentially what you have is, in a simple picture, a transition from the linear structure that you have once translation has finished, and this folds in a number of steps that we can, in a minimal way, think in terms of small modules that fold independently, the protein domains. Okay? In the literature you can follow on this, you will see that actually this can be seen as a kind of a thermodynamic problem, okay, where you have an energy function, and what happens in the protein folding process is energy is minimized over time. So you will have, for example, this state here, and a final configuration here, which essentially can be described in terms of a minimization process, and with an energy function that, as you can see, kind of reminds us the potential function we have seen before. So what I want to do in this lecture essentially is to provide the basis of how do we solve this kind of problem. And the thing is that if you think in this simplest scheme here, okay, what you can see is that I have three differential equations that describe the population dynamics. The first is simple. It's just a transition from the first state to the second. We will assume that this is all that happens. There's no decay, there's no degradation, okay? So it just transitions. So my second class of molecule, for example, will be described in terms of population dynamics as follows. On the one hand, everything that disappears here goes into this compartment. And on the other hand, since this makes also a transition with this rate into the last compartment, proportional to the population, okay, I will have an extra term. And finally, there's a third population that just receives the outcome of this decay here, and that would be all, okay? Through linear equations. That's, in principle, easy. But as you will see, we need a specific mathematical tool to actually solve this. The first equation is no problem. We have seen this already. This is the exponential decay. For this, we know that the solution has this form, exponential decay over time. All right, what happened then, and that's the crucial part, what happened with the second equation? Well, we know now that A can be calculated independently, all right? So we can actually use explicitly its form, and we end up with an equation, a differential equation, that has a time-dependent part here that cannot be separated. We cannot just put in one side b's and in one side time. We cannot. So how do we solve this? All right? Well, let me do the following. First of all, I can rewrite this for convenience, okay, in this way. I just moving terms, okay? All right, the way I written this belongs to a family. This is a specific case of a family of equations of this form, and I'm going to solve this. Oops, sorry. Okay, so in other words, I have my x function that I want to find out, right? I want to solve this, and two functions, okay, that in general will be time dependent, right? I'm saying in general because this clearly is a time dependent function. This is a constant, right? Which is a kind of a limit case of a time dependent function. In general, that this could be a time dependent thing. This specific case is a constant, good for us. But that's the general equation that I want to solve, right? To do so, I'm going to use a particular mathematical trick, okay, which is the following. I can think in this function, that's what I'm looking for, right, as a product of two functions, right? I can always do that. I think in any function you want, t squared or whatever you want, you always can write down in terms of two different functions in infinite ways, okay? So this particular trick will allow me to solve in general this equation, okay? How can I do this? Let's use this expression and use the chain rule, because I need to put the derivative of x as a function of time. And that would be, as you know, this term here, the derivative of the first by the second, and then this part here, right? I want that to be my expression for x, u, v, and there's the derivative. So I can use that, all of it here, right? Replacing the derivative of x over time. Oops. Then I have my function in general, phi1. I will use phi1 without the t. We know it's a function of time. Now x is ub, right? And phi2, sorry, let's just put it this way, okay? All right, so now from this expression, I can rewrite it the following way, okay? This here is in fact nothing but this. All right, so let's impose something here. Since my function, the function I'm looking for is just u by b, and the first function I'm going to find out is v, which is arbitrary, I can say that this has to be 0. Okay? I will impose this condition. All right? So if I do that, what I have is a differential equation that I can solve. Okay? Sorry. Yes, this is. Okay? I can solve it because I can separate variables. Now I can do it. This is nothing but what we already saw when we did the first kind of problem, the exponential decay. And I can integrate this. Okay, is an integral I can do straightforward, and this is just this integral. It will depend on the value, the exact form of phi1 plus a constant. All right. So, who is v of t? As you know, I just need to take exponentials in both sides, right? Will be an exponential that I can rewrite in terms of a new constant. So this is v. Actually, I could even simplify more. I'm still in the process of finding out the first part of my whole solution, right? I can make some more arbitrary decisions. For example, setting this constant to 1. Okay? So I have my first part. I know it looks clumsy, but you will see you can use that in a systematic way. Okay? So this is for the first part. Now I have to find out the second, right? But I have imposed something. I have imposed that this part is 0. So actually, what I only need to solve is a differential equation, right? That contains only this term and this term. All right? Let's do it. So we are almost there. This is the form that we just derived from the condition that we imposed about x being the product of two functions. We have imposed that this quantity is 0 and find out v. And now, since we impose this condition, you can see that there's a remaining differential equation that I need to solve, right? Made by this term here plus this term here. Okay? So now I know who is v, this function here. Okay? And I can again separate. So I will have in one part my differential for u, and in the other part I will have phi2, whatever it is, v that goes into this part by changing this sign. Okay? And time here, right? So as you can see, I can also integrate these, right? For each case, who is phi1 and phi2, and I'm done, because what I have is that my second part of the function, I should use prime as here, but I'm just ignoring this, plus a constant. Now I have to keep the constant, right? This is not a place for doing more arbitrary decisions. Once I fix that, everything else has to be maintained. And so what we find out is that the general solution for the differential equation is as follows, right? This term here, this term here, plus a constant, okay? With this solution, we can actually apply it to any problem that we decide to solve that can be described in terms of a chain of events that involve transitions from different states, right? Okay, let's do an example to see that this looks like a complicated expression, but it's very easy to use. In these reactions, as you remember, we could solve this directly, and we had here a problem that we can write in the following way to see that it belongs to the same form. Right, we saw it before. You can see very easily, and we already said at the beginning, that this is exactly the form that we want, right? It will be my phi 2, okay? And for this particular case, we are lucky, this is a constant. This is my phi 1, right? Let's see how this applies with this expression, right? And how do we get my B population, right? So let's look at this. We can actually follow step by step. Since phi 1 is just a constant, this will be the integral of k2, so easy, just a constant, right? Inside this expression, I have again the same function, except that is positive sign, okay? Now phi 2, right, which is this term here, right, and C, right? I didn't mention that, but the constant C typically will use it, we'll find out exactly its value by looking at the initial conditions, right? So C is arbitrary, but we can determine it. So we are almost there, okay? Just to make an intermediate step, this would be an easy integral because this is a constant that I can keep outside. You see that here is in reality this is just that constant, and we can just take together k2 and k1 in this way. So solving this is easy. k2 minus k1. We need to integrate the exponential, which, as you know, is the exponential with this correction here, plus C. And that's it. That's our solution. This is the general solution. We want the specific solution for the problem, knowing that we have an initial condition. We didn't mention that, but let's assume the simplest scenario where A at the beginning was the only molecule present, and then B and C were 0, okay? Initial condition, A of 0, 0, 0. That will be for B and C. If that's the case, right, we can use this expression to find C, because when time was 0, this was 0, okay? This is just 1, this is just 1, right? And it's straightforward to see that my C is just this number with a minus sign, okay? To avoid all these numbers and constants, just call this omega, and since for t0 B was 0, we find that C is minus omega, okay? And we are there, because now the final solution for B is just what? We can actually make it nicer, right? This is omega, this is minus omega, okay? And we multiply everything inside. We will have a k2 here that goes, and a e to the minus k2 appears here, right? And you can check that what remains is this here and this here. This is B of t, okay? So general expression, straightforward to use it to find out B, okay? How can I find C? Well, there are two ways of doing it. One is follow exactly the same criterion, because for B, you will have here a differential equation where now we have a single function, time dependent, so allows to separate. You can integrate, right? The other way around is, since I know that the system is not losing anything, the number of particles is going to be the same all the time, eventually, at any time step, the total sum of my populations, right, is going to be a constant. Okay? So that's for any time. So C is nothing but the total amount at the beginning, right, that keeps constant over time, minus A of t minus B of t. You do the integral, you check that this is correct, all right? Very good. If you look at the, if you want to look at the graphic expression of this, it's very easy to find, because essentially it's two curves that go like this. A will decay exponentially, right? And remember, this is the maximum value that you can find. Whereas B and C will behave like this. B will grow eventually, but it will eventually also decay, all right? Because it's created, but also decays. And finally, oops, sorry, this is for B. Okay, this is for B. And C will go up, 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 until eventually, and that connects with our intuition, eventually it's going to become the single kind of molecule in the system. All right, this can be applied to many different case studies, right? I mentioned at the beginning the colon crypt as a particular module that you observe in tissues. And can we make a simple model of this kind of system? Well, let me make the simplest set of assumptions, right? Again, every time we make a proposal for a toy model, we simplify the system. But let's assume the following. Let's assume that a minimal model of the colon crypt works like follows. Stem cells, I'm going to assume that this is a constant compartment. It's not true. Stem cells also renew, okay? But let's assume that it's constant, okay? So that I produce, I'm going to keep my K1, my K2. No, let's not keep it because it's different. Let's say eta. This becomes or generates transient cells, right? My compartment of cells that then differentiate into a kind of cell that does not replicate anymore, whereas this compartment, I can assume that I have some replication rate, right? That's the transient cells, okay? And also that also with some rate, let's call it gamma and beta. Now let's use for decay as usual, the delta, right? That will be my transition system, okay? As you can see here, I introduce an extra component, right? It's not going to be a problem in terms of formulating the system as defined here, right? That involves replication, okay? And what I want you to do is to formulate this problem in terms of differential equations. You'll have two differential equations here because I assume that the stem cell compartment is just constant, right? But you have nevertheless to use this formalism to find out the final solution. And one of the questions I want you to address is under what conditions this would be a homeostatic system, right? Because as you will find out, it could grow to infinity under some conditions, but of course we don't want that to happen. And for those of you who want to go a step beyond that, there's a very interesting paper in PNAS by Johnson, Maney, and others, where they actually do the more general linear system, where stem cells renew, where each compartment has a given set of parameters, and they use this not only to think in terms of how the crypt becomes homeostatic, but also under what conditions, as it happens with the emergence of cancer in colon cancer, in what conditions you observe that multiple transitions that you need to go into a fully carcinogenic system.